how do we know what the evidence is for inflation?
That's a really good question. So I didn't yet mention inflation, but it's something I work on in my research. So I said that the universe is growing, but I didn't say how the growth starts. The growth started in the beginning. And one of our ideas that's only a partial explanation, is that at the very beginning of the universe, there was nothing around at all except for this energy in space that we call the inflaton field. And the energy in that space grew really fast in this thing we call inflation. For a fraction of a second, trillionth of a second, space grew actually faster than the speed of light. There are a few reasons why we think that it kind of works. And one of our favorite reasons is that it actually produces the seeds of everything we see now. So what I didn't get to explain is that, the stars and galaxies had to come from somewhere. And actually, we think that there were tiny features in the early universe that maybe were put there by this process called inflation that then grew to become the things we see now. All the features we see when we look at both the features in the universe and we look back to actually this light coming from the Big Bang, that's what I study, it all looks consistent with this story. What we're looking for now is actually gravitational waves injected into space at the time of the Big Bang. People may have seen results from the LIGO experiment recently, where two colliding black holes distort space and make it ripple and send out ripples in time, where actually the room actually would be growing. If a gravitational wave passed through us right now, then the whole of this lecture room would grow a bit as it passed through. So we've seen them from black holes. If inflation happened, this initial very energetic expansion of space, it would also inject gravitational waves. So actually, believe it or not, the experiment that we're building in Chile, the Simons Observatory, that's one of its big goals, is to look for gravitational waves from inflation.
Okay, any more for any more? Right in the middle there, can you see? There's a lad in the second row down. Tell you what, you go and get a microphone to him, and between that, we'll find someone who's a bit closer to an aisle. So stick your hands up again if you've got another question.
So, will we eventually not be able to see anything? Because if stuff continues going faster and faster, and if at the Big Bang stuff could go faster than the speed of light, that means it could happen again. Doesn't that mean that it would eventually start going faster than the speed of light?
That's a really good question. The answer is yes. So it's a really good question. So if, as we think is the case right now, space is growing faster and faster, then yeah, that does mean that very far in the future, all the galaxies the beautiful galaxies we see in the sky, they could vanish over this cosmic horizon I mentioned earlier, which are the things that we can actually have access to. And we would then, again, think that we were alone. Now, for a while, our own galaxy would still be there, but then it might get ripped apart too, depending on how strong the universe is growing. So we're not quite sure about that last bit. But yeah, it won't happen for a while. But it's a really good question.
Okay, can we not make this too depressing, all the end bits of how we're all going to die in the end? Okay, right, we've got another one up there somewhere.
Hello? Oh, yeah, thank you for the talk. I've got a question. Aside from dark energy and dark matter, what are some of the other big problems in astrophysics that keep you awake at night?
Because they're not big enough.
Not big enough, not big enough. Probably the main questions that keep me up at night are dark matter and dark energy are two of the main questions. My third question, actually, we just talked about, which is, why did the universe begin to grow in the first place? Because we don't know why. And even if this thing that we call inflation, which was this energetic expansion at the beginning, happened, why did that happen? And can we ever, what's the furthest we could ever look to try and understand where it came from? There are some wonderful ideas right now, alternatives to this model for inflation for the beginning of the universe that talk about something called a cosmic bounce, a bounce in cosmology, where the Big Bang is just the things shrunk and then bounced apart to produce the growing universe we see now. So certainly it's the case that when we talk about the age of the universe, we are just talking about the time since the universe we can access began to grow. that doesn't mean that there was nothing around before, and it doesn't mean that there's not stuff elsewhere that's not really in our universe. So we're quite limited in what we say when we say the age of the universe and the beginnings. But those are my main concerns. There are other things that I find fascinating, but well, actually, what really keeps me up at night is how to make sure I don't have systematic errors in my measurements. But that's
the truth about science. Okay, someone on this side. Oh, there's up in the back there. I can see hands up at the top. And then after this, it's your turn. You've been very quiet. I want some questions from over here.
So, when we're looking at the elastic band.
Mm-hmm.
When you said that the Big Bang, all those little blue dots would join together, what would those blue dots actually consist of?
That's a really good question, because actually it's quite right that as you wind time back, we don't expect that at the beginning, when the blue dots were on top of each other, that they were actually galaxies at the time. So we think that if we could wind time back, that if we could go back to when they were on top of each other, that they would just be fundamental particles. At the very, very first instant, they might be particles that we don't know of yet. But just after a fraction of a second, they would be protons, neutrons, rays of light, neutrinos, and we think these mysterious dark matter particles. And it would just be this sea of those things. And then what would happen is that they would form hydrogen and helium atoms. And then over millions of years, little lumps in that soup of particles would be pulled together by gravity until after a few million years, hundreds of millions of years, those big lumps could ignite to form the first stars. And then they pull together to become bigger galaxies. So the galaxies we know of, these blue stickers, have been around since, half a billion to a billion years into the universe's history. It's a good question.
Okay, your turn. Questions from this? Yeah, in the middle there. We got sorry, you're far away up there.
Is dark matter and dark energy related in any way?
We don't know. Again, good question. There's no reason beyond their name. No, they seem to be quite different things. This is an interesting idea. The simplest explanation right now, although maybe it's not simple, is that simply dark matter is a particle we haven't discovered yet. Whereas the simplest explanation for dark energy is the energy of empty space. So we think they're quite different. But when you don't understand 95% of the universe's energy, which actually I didn't quite mention, the dark energy takes up 70% today of all the energy in the universe. It's pretty big. When you don't understand that much, you have to have in your head that maybe you've got a bigger problem. Right, so I think it's not inconceivable that we will find they're connected. And maybe we'll end up with a big paradigm shift where our whole picture of the universe and how it works changes significantly. I don't think we've got wrong what we're seeing now, but our interpretation of it might have to change, and maybe they are connected.
So you've had your hand up for a while there, down at the front here.
Is it possible you could give us an idea of how fast these things out in the universe are changing? So we saw the Eagle Nebula.
Yes.
I mean, how long ago was that taken? And then if we were to look in the same area of space, would it look vastly different now?
Oh yeah, no, that's true. So the time scale would be it's interesting. So the time scale is kind of a bit related to how the life cycle of stars, just for context. So for example, again, I said that stars like ours will live for 10 billion years and won't change. But more massive stars actually go through their life cycle much quicker, in hundreds of millions of years. So you might have lots of big heavy stars exploding and disturbing those kind of environments. So the time scale of that would be then millions of years. Now there are other events that happen much quicker. The single explosion of a star takes place in just seconds, hours, days. But in terms of disrupting these things, it would be more like millions to billions of years.
Okay, and then up the top there somewhere. Yes, yeah. And then there's another one on the balcony after that. You just bear in mind how long this takes, and then really think about what it means for something to be 100 million light years away.
So essentially, you mentioned that it would take about 4 light years to get from Neptune, for the light to get from Neptune to here, right?
5
Now,
hours. 5 hours.
5 hours.
Yeah.
Sorry,
That's
5
fine.
hours. Now let's say that if you managed to build a spacecraft, for example, that could approach the speed of light or reach the speed of light, right? Time would be relative, wouldn't it? So if that's the case, how much time would pass for the people that are on the ship in comparison to the people that are on Earth? And would it still be the same amount of time? And keeping that in mind,
Yeah.
would we be able to go even further considering that their time would be much slower?
That is a good question. And so it is true. And I think this is one of the most marvelous things about physics is that you do discover that time passes differently, how quickly you're traveling or how massive an object you're near. For example, if you go near a black hole, your time will pass slower and you won't age so much as if you're not near a black hole, but you wouldn't survive very well. But and so, yes, time will pass differently to a traveler near the speed of light. It wouldn't pass differently to us observing it from here on Earth because we're stationary. So I think it's an interesting idea, but the idea of getting us to near the speed of light is a technology far beyond where we are right now. So yes, you're right, time would pass differently. And there's this famous twin paradox. If you send a twin off on a rapid spaceship and it comes back, it will be a different age to the twin stationary on Earth. But I think our technology is not such that we are anywhere near that kind of speed.
Has anyone worked out how different the time on Voyager is to our time here on Earth? That would be an interesting
Probably,
thing.
but yeah, it's...
Put that in the list of homework
Yeah,
somewhere.
exactly.
Okay, right, up on the balconies, up there.
You said that dark matter passes through us
Yeah.
all the time, and so do neutrinos. They always pass through us. And I read this article in the New Scientist, which said there might be another type of neutrino other than the three we already know, called a ghost neutrino. They couldn't think of a better name.
Yeah.
But how likely do you think that these ghost neutrinos exist?
It's a really good question. It's actually something I'm doing right now in my research. So one of the things that I do is I try and actually measure the number of neutrinos through their impact on the behavior of the universe. And so we're looking, there's one possible additional one there may be ghost ones as well. There's one that's called a sterile neutrino that doesn't interact. That's one of the numbers I try and measure as a cosmologist is how many it is. And at the moment, we're kind of down to the fact that it's 3 plus or minus 0.3, where plus or minus means how uncertain I am. So right now, when I look at the cosmology data that I collect from my telescopes, we don't think there's room for a whole other regular neutrino particle, but there's room for maybe a little bit of one that behaves a bit differently. And actually, with the telescope I'm building now in Chile, we're trying to narrow down any extra neutrino to figure out what it is. But it's a very interesting idea. These are the lightest particles in the universe. Billions of them are going through your hand right now, more than probably even this heavier dark matter. And we don't understand it very well at all. So that's something that I think is fascinating.
Okay, where are the microphones? Let's pick someone that's close to the microphones. Anyone? Oh, on the back row, right next to you there. Anyone else from this side? Oh, yeah, okay, and then it's next time be you. Yeah.
What's your favorite explanation for dark matter and dark energy? Like, you personally, what you, speculatively, what do you think is more, likely?
Well, I think for dark energy, I think the energy of empty space is the most likely because it's already kind of in our equations. Oh yeah, okay, so this is a question. So here, there's a problem. I said it might be the energy of empty space. There is a problem that if you try and work out, so empty space isn't really empty. Quantum mechanics tells us that there's constantly energy being created and annihilating in any bit of empty space. Empty space actually is like bubbling with little bits of energy, creating and vanishing again. And if you try and work out how much vacuum energy there should be in empty space, then the amount is many, many, many times different to what we observe. And so the fact that we see this specific amount today, we don't have a good theory to explain it. So we definitely don't have a good theory to explain why empty space should have this amount. But my sense is that it probably is that, and that we need a better idea about why. And that's partly based on observations. Well, this is related to okay, so if this dark energy is something different from empty space, then it will kind of affect the way that the universe is growing and the way that big clusters, cosmic structures group together. And we're increasingly improving our measurements of those, and we're not finding anything that indicates anything different from just the energy of empty space. But it may still be there, but that would be my favorite idea. For dark matter, I would have used it 5 years ago. I would have said to you, oh, I think it's this supersymmetric particle. There's a theory that comes up that says all of our particles should have a super partner in this whole sector of particles we haven't found yet. I would have said that 5 years ago, but we haven't seen it at the Large Hadron Collider, so I think it's something different. And I think that probably it's a particle, but it might be a whole family of particles. So yeah, right now I'm a little bit stumped on that one.
Save room on the family tree.
I have a question.
There's a lady up there on the second row back. Yeah, who said was going to go next. Where's the microphone that was up there? Oh, it's over there, is it? Okay.
I've got a question. What we see is in the solar system, matter is concentrated in small areas. In the galaxy, it's concentrated. You talked about superclusters, where it's very concentrated. So the universe is completely heterogeneous. It's not homogeneous at all.
That's right.
And we can look out from into all different directions from us, but we are still stuck in this area, in the region of the universe that's around us.
Yeah.
And that has a certain density, and that's different to all the other areas of the universe in the distance, isn't it?
Well, actually, on average, no. So this is something that on average, yes, we're seeing some regions that are more dense or less dense than others. There's holes between these galaxies and clusters of galaxies. But on average, it averages out over the observable universe as being approximately average. But also the thing that I didn't really have a chance to talk about this, the thing that I look at is actually, if you go back and you can see the universe as we're able to do, actually when it was very young, only 400,000 years old, which is a picture that I take with the telescope I showed you at the beginning. If you go back to that point, the universe is almost featureless. It's the same density everywhere. It has features that are only 1 part in 100,000. It's uniform. And so we actually can see back to the point at which there were no features, and the whole of the universe that we can see was just the same everywhere. So we actually can trace the growth of these tiny features to these big, some parts of space end up as a big void, empty of stuff. Some parts end up as a big heavy part. But we've done that now, and we've seen that evolution. And that to me, that's it's extremely compelling.
My question was going to be.
I thought you'd ask your question.
Can you make it very short, because we've got other people waiting to ask.
Wasn't it?
Okay, up here. Where's that microphone gone up here? Yeah.
A slightly different question. I've decided that astrophysics is what I want to do. So are there any British universities you would recommend?
All of them. There's loads of astrophysics going on in many departments. The way I would look around is look on websites and see what the researchers are doing, because there are courses in many of the universities in the UK. Mostly you would start with physics. You can start doing astronomy. I started and Helen started doing physics, and then you can specialize in a given area. I think that's great, because even if I'm biased and I say, yes, do astrophysics, I think actually if you like doing physics, you should study it and then decide what you want to do, because there may be something that you haven't come across that you think is truly fascinating. So, but I recommend as well looking on websites and seeing what the researchers are doing and see what grabs your interest. But yeah, that's great.
And building instruments as well. Everyone always forgets that you can only do with the science. I'm an experimentalist, does it show? But because people build the instruments, and one thing we do have in the UK is a huge amount of expertise at satellite build. You can probably say more about that.
Yeah, no, I think that's really true, and that's I second that. That building stuff. And I feel, because I analyze data from telescopes, and the only reason I can do that is because my colleagues develop these extraordinarily sensitive cameras and the telescopes to do it. And I kind of am slightly regretful that I can't do that myself, right? I just take the data and turn it into numbers, and yeah.
Okay, we haven't heard from the balcony in a while. Up there.
Thank you very much for your talk. I was just wondering, you said earlier about the limit of
It is working.
the limit of the observable universe being much larger than the age of the universe.
Yeah.
And I was wondering just how that worked.
Oh, yeah, no, that's a really good question. So if the universe weren't growing at all and it was just static, then the distance that light can travel in 14 billion years is 14 billion light years. But actually, if space is actually growing at the same time, then the distance actually gets to be bigger, because the space in between, as the light is traveling, the space is getting bigger and bigger as the light's traveling. So it ends up having further to travel than it would have done if the universe were not growing. So it's kind of a neat calculation that we get our undergraduates to do when they first do cosmology, is work out the distance of something in the expanding universe. And for a simple universe just full of dark matter, not that simple, but regular matter, it turns out to be exactly three times the age of the universe. So that would give you like 45 billion years, but then this dark energy makes it a bit more. Yeah.
I'd never thought that was what Usain Bolt was doing before, but now I'm never going to see that again without seeing you doing that. Okay, where else have we got questions? A lot of bright lights. Up here? Where's the nearest microphones? Up here.
I think that last question was probably my question, which was, I was going to ask you to expand on what you said briefly during your lecture, that although the universe is 14 million years old, it's actually 50 billion years old.
Oh, it's not. No. But I'll expand on that. Sorry. Ask a question. Shall I expand on that?
Yes, the question is, you said that the universe is 14 billion years old, but then you said, well, actually, it's 50 billion years old.
Let me be clear.
Yes.
The universe is 14 billion years old, give or take a bit. But the radius, the distance to the edge of the observable universe, is more like 50 billion light years. And that's because the distance to the edge of the universe is the distance to the edge of a universe as it's been growing. As an aside, the definition of distance is a little complicated in cosmology. Another thing we teach our undergraduates is, distances don't really mean, you have to be very careful about what you mean by distance if the distance you're measuring is growing as you're measuring it. And maybe your ruler is growing as you measure it as well. So it's kind of fun, but the broad picture is that I'm not saying, I'm definitely saying it's 14 billion years old, but I'm saying the distance in a growing universe that light can travel in 14 billion years is further than 14 billion years. It's roughly 3 times further. Yeah.
Up here, wherever that one's gone.
Brilliant talk, thank you. Is the universe expanding into anything? And are there any clues from the early universe as to what potentially is on that border?
No, it's not expanding into anything. It's a good question. So there's a limitation to my model of the 1D universe, one-dimensional universe, which is that this elastic clearly has some ends. But we think that the real universe is, if it were one-dimensional, has 2 options. The 2 options are either this piece of elastic is infinitely long, it stretches on forever, each direction, or it's connected up like this. Okay? Quite possible. And so when we go to 3 dimensions, it's possible that the universe is connected up in 3 dimensions too. Now, you need a 4-dimensional brain to picture a 3-dimensional universe connected up, but we can do it a little bit. So imagine you're connected, a bit like a donut. So a donut is the next level up in 2 dimensions. You connect, if you take a piece of paper, you can wrap it up into a tube, and then you can wrap it round into a donut. And that would be a 2-dimensional space that is kind of finite. The surface of a donut is finite. And so it's possible that the whole 3-dimensional universe is finite too, such that I wrap up each end, which means that I connect up these bits, and I connect up these bits, and I connect up these bits. The fun thing about that is that any direction you set off in your spaceship, you'll eventually come back to where you started. And we don't know which it is. What we do know, and this is something, again, that I do in my research, is that we know that if it's connected up like this, that the size of the universe that's connected up is bigger than our observable universe. Because if it was smaller, this wonderful thing would be true, which would just be awesome, is that it would be like being living in a hall of mirrors. We could see the same thing in our universe multiple times, because we'd see an image, it would come from something, it would go all the way around the universe, come back, and I'd see it again as it was further in the past. So I'd see the same repeated image out in the universe. We don't see that. So we know that if it's finite, it's got to be that big. If it's not finite, it's infinite. It doesn't have edges. And this is this thing so we think, and the connection to that is that often people think of the edge because they think of the Big Bang as coming from somewhere and shooting out to an edge. But we really think that the stretching of space that the Big Bang produced is a stretch that really did happen everywhere, like the elastic isn't growing from one place. So we can just imagine shrinking an infinite universe down, and it's infinitely smaller, but it's still infinite.
While you're all wrapping your heads around that. So we've got a few minutes. I really want to encourage people who haven't asked the question or who think their question isn't clever enough, because we've had a lot of quite complicated discussions. If you are a bit worried about asking a question, ask it anyway, because you won't be the only one. We've definitely got one up there. I can see a lot of waving going on. Over, where is it? Can't see. Ask away.
Have we moved away from just the explanation of a single inexplicable event? Are we looking at multiverse things? Are we looking? Is it there? I heard there was an anomaly in the cosmic microwave background, and does that show a connection possibly to another universe?
It's a good question. So there was some ideas a little while ago that maybe we're seeing features in this very old light from the beginning of the universe. Those are not there convincingly, and there was some claims that they were there. They're not there. I work on this data, and they're not there. But there is definitely still. I'm sorry, I'm looking. I didn't see where the question was coming from. I just heard it.
Came out of the spotlight.
I know. It came out of nowhere. Oh, up there. Cool. Great. Okay. So it's quite possible, and I know I didn't get to mention this, that it's possible that part of the universe inflated quickly to become, and expanded quickly to become, the bit of the universe we live in, our whole observable universe, and perhaps far further. Another idea is that other pieces of the universe, very far away from us, would have started expanding at different times to ours. And this is one of the ideas that we call the multiverse, which is that there are actually many different, you can get sort of inflation happening, a growth of the universe happening at different times in different places. And they would have different conditions inside them, and they would then be kind of their own universes. That is still a possibility. It's actually one of the reasons that some scientists don't like the idea of inflation, because the argument goes that you would then get so many bits of the universe blowing up to produce kind of arbitrary range of physical laws, that the possibility of getting one that looks like ours becomes very unlikely. But I think the answer is that that could be the case, and we don't know. And it's going to be hard to find evidence for it. We do look in the cosmic microwave background for it, but I'm not convinced by any evidence yet.
I think we've got time for one more question. There's someone over here, on the edge here. Yes, if you go.
That's very interesting. Is there an explanation for the disparity in the age of the universe calculated from the CMBR and from Hubble's constant?
That is a really good question, and it's something I'm working on right now. So right now, okay, when you look at the galaxies expanding around us with these Cepheid stars, we get a number for how fast the universe is growing, and it's a number that's 73 kilometers per second per megaparsec. What does that mean? It means that galaxies are typically separated by about 1 million light years or so, about something that we call a megaparsec in units of astronomers like. It means that typically a galaxy that's one galaxy over from ours would be moving away from us at 73 kilometers per second, and one that's twice as far would be moving twice as fast. When we go and study the data, this relic light that we can see actually from the Big Bang itself, where we're actually doing the biggest, I talked about big triangles. When we look back at the edge of the observable universe to 14 billion years back, we actually measure triangles that are 50 billion light years long. And doing that, we end up with a number that's 67 or 68 kilometers per second per megaparsec. And they differ by more than the uncertainty in the measurements. And it's fascinating to us in cosmology right now. We're not sure whether it's different because these two different numbers are different because one of the experiments has an error that they haven't accounted for, an uncertainty that they haven't properly included, which I think is reasonably likely, having worked on one of them. So I worked on the Planck satellite, which made the one measurement. Or it's actually that we have the model for our universe wrong, which would be fascinating. And the possibilities that there are things that could happen, like neutrinos could behave differently to what we expect, or there could be extra particles that we haven't come across yet, or something weird's happening. Actually, with the telescope I showed at the beginning, right now, what I'm doing right now is I'm trying to make an independent measurement of the expansion rate from the CMB, from a different experiment, to see if there's anything we can understand more on that. So I think it's exciting times.
Well, that's a great point to finish on. So Jo will be outside immediately after this with copies of her book. So I encourage you, it's fabulous, I've had a quick look through. I encourage you to buy that, get Jo to sign it. And before you go, please join me in congratulating Jo on a fabulous lecture.